So for this example, you're going to use some of the, as you can already probably notice, but if not, it's fine. You're going to use some of the basic rules for integration. This is a definite integral, meaning remember that there are two types of integral. The one that you don't have any bounds here, and this is indefinite integral. It's also called anti-differentiation, and the answer to that is a function. You have a variable in the answer, and then the answer to definite integration, it's a number because you're calculating area. So in a way, this is more of a real integral. Okay, so you want to first get a graph of this function, and you can use Desmos, right? That's the function. Okay, so 0 to 1, I screenshotted the portion that I need. Then you kind of mark the boundaries, and you're trying to find area under this curve. So this is the area that you're after. Well, you can divide that into a little rectangle and a triangle, right? And before calculus was developed, the way that people solved this sort of a problem, well, they didn't solve this type of like curve under the area under the curve. They didn't know how to calculate that. But if it was a function like this, a horizontal line, area under that function, it's a rectangle. You don't need calculus for that. Symmetric shapes like these ones, you know how to how to calculate area under those, right? So I'm gonna calculate area in this like pre-calculus way and see what my answer is so that I know the ballpark. So I need the height of that, I need the height of this rectangle, and the width I know for both the rectangle and for the base of the triangle, that's 1 because it's 0 to 1, right? And the height of this rectangle is 1.5. Okay, 1.5 times 1. Area of this rectangle is 1.5. Area of this triangle is here. If this is 2.5, this is 2.3. 2.3 minus 1.5. The height is 0.8. Okay, 0.8 times base divided by 2. That's 0.4. Okay, if you added that, the total area would be 1.9, correct? Okay, so you should expect the answer to this definite integral to be, obviously it would be a number, and hopefully that number is close to 1.9. If it is close to 1 or if it is close to 3, you know you made a mistake. And if it is close to 200 or 2000, you know you made a big mistake, right? So that's a very good way to, anytime you have any curve, you can kind of see a little bit a kind of a rogue way of doing math, right? Like before calculus, and you can assess what would make sense, what answer would make sense, and what answer would be total nonsense, so that you can catch yourself in making a mistake. Okay, so obviously we're going to use calculus here because that's what we're doing, and I'm going to separate the numerator here. So I'm going to write two fractions being added that share denominator, so they can be written separately or they can be written together. Just like so. Why did I do that? Because you can, what integral is, it's area under the curve of a given function. But you can, with integrals, separate this and have an integral here with dx and this integral. The reason why you can do that, it comes from linearity of integration, because you can calculate area under this function, under this curve, and then add them separately. That's exactly what I'm going to do. This is exactly what you always do because it just simplifies everything. Okay, so I have written two separate integrals that I'm going to take. Oh, also I forgot bounds here. Excuse me. I recognize that this is arcsine. If you look at your formula sheet of your basic integration rules, you will see that its arcsine is integral from du a square minus u square. Your a square is just a number. Here it is 2 square, right? So I recognize that's arc sine. I also recognize that if I made this to be u, then this will be du because I have x squared here, and I know that derivative of x squared is gonna still leave me with 1x. So I have 1x here sitting, so that's clearly du. So this kind of this x kind of helps me see that they've given me ingredients for du, so clearly I'm going to go with u sub. Okay. My u is all of that, whatever is under that square root. Obviously, I'm going to need du, which is derivative of u. Derivative of 4 is 0. Won't write that down. And derivative of negative x squared is minus 2x dx. I also like to go a step forward and outline and separate what I have here is not negative 2x dx. I only have x dx. So I'm going to take a little extra step and write that down so that I have that ready. Wherever I see x dx, I will substitute that with du over negative 2. Now I'm going to change boundaries. Why I'm going to do that? Because I don't want to go back to this variable, because dealing with u, square root of u, is easier than dealing with this whole expression under square root. And usually when you don't have definite interval, you have to go back to your original variable that the problem had. But in this case, my answer is not going to have variable in it. My answer is going to be a scalar quantity. It's just going to be a number. I'm calculating area. So obviously I'm not going to have any variables, so I don't worry about going back to original variable. And I'm going to do what is the simplest, and it is simplest to change the boundaries and never go back to this original expression. So 1 here, I'm going to do u, and then here, right? I like to do upper bound first, lower bound second, and I like to put original bounds as sub for u. And the relationship between u and x is given to you by this expression. So 4 minus, instead of x, you put 1 in this case, 1 squared, right? And that's 3. And for the lower bound, I don't want that, you put 0 squared, okay? That's 4. I have completed my u substitution. I have my lower bound, which is 4, my upper bound. I have 1 over square root of u, and I have du over negative 2. Now, du over negative 2, that's du times negative 1 over 2. I'm going to bring that out of the integral because that's simply a constant so that I don't have clutter in the integral. I'm also going to rewrite this integral into this form, because there are certain integrals, for example, this one, these ones, x, it has some type of a fraction as its power. It's best to rewrite it like this, so you recognize that you're going to be using power rule, where the power of x, n, your n is this whole thing, and you treat that as n, you treat this as n, and then you go forward with your power rule, you simplify it, and this will be the answer to this interval. And there are several that you kind of want to have it in a separate paper solved. You can screenshot that. So I'm gonna rewrite this as gonna bring u out of the basement as with a negative attitude, so negative 1 over 2, right? And it was square root, so 1 over 2. And I'm gonna rewrite this integral, but I'm gonna do something, at least change it a little bit so that it looks exactly like arc sine. I'm going to say 2 squared minus x squared dx. Not going to forget my bounds. Okay, now I'm going to take both of these integrals open the square brackets because I'm going to need to have bounds. So I have u to the power of negative 1/2 plus 1 because I'm taking this integral. All of this from 4 to 3. Now positive 1 minus 1/2, that's simply positive 1/2, right? So I'm going to say 1/2 and 1/2. Notice here that 1/2 divided by 1/2 is same as multiplied by 2 over 1. 1/2 multiplied by 2 over 1, 2's get canceled. So you can cancel those. And I'm going to take this integral as well. Not going to forget that constant. Arc sine, so arc sine over 2 because the formula has u over a. A is 2. Zero to 1. I don't have 1/2, but I do have a negative sign. And I'm going to do here, instead of having u to the power of 1/2, I can go back to square root of u. So I'll have square root of 3 minus square root of 4. This is already applying fundamental theorem of calculus, upper bound minus lower bound, minus here, upper minus lower, always. Anywhere you have x, you substitute upper bound first, what I did. You substitute upper bound first, and then lower bound. 0 over 2 is simply 0, so I'm not going to write over 2. I'm going to do a little analysis here. So I wonder what arc sine 1/2 equals to. It equals to a number, right? In radians, because, so I wonder what arc sine 1/2 equals to. Let's say it equals to x. Sine of what angle is 1/2? When is sine 1/2? It's 1/2 at 30 degrees, right? But all of these angles, trigonometry with integrals, it's always in radians. So don't think of degrees when you're doing integrals and you see trig, it's always angle in radians. And that will be 1/2. Okay, your x we determined is over 6. This whole thing, arc sine 1/2 equals to pi over 6. And what does this equal to? Okay, same thing, right? Arc sine of 0 is question mark. And sine of x is 0. And when does that happen? Sine of 0 is 0. If you had arc cosine 0 there, this wouldn't equal to, that wouldn't be same as 0. It would be pi over 2 because cosine of pi over 2 is 0. But you have arc sine, so you don't have to worry about that. Okay, so I will do square root of 3 plus, because minus 2, I'll take square root of 4 plus, as we said, it's 3 times pi over 6 minus 3 times 0. So I'm not going to write that because we said this was 0. Okay, these get canceled. Okay, negative square root of 3, that's around negative 1.7 plus 2 plus 1.57, 1.6. Okay, that's actually 1.9. That's the final answer. Look how close, or we estimated it exactly. However, if you get more sig figs here, if you use calculator to calculate square root of 3 and pi over 2, you will get an answer that's not exactly 1.9. You'll get more precise number. But we were able to estimate this with great precision and accuracy, not precision, accuracy. So this is how, so let's review what we did. So obviously we did this in a rogue way so that we could see if we're getting the answer once we do all this work, if our answer makes sense, right? Then we separated the numerator. We wrote it as two separate functions. We recognized that this was arcsine. Then we recognized that there was fraction of du given, so that hinted at to us that we need u sub for this interval. We did u sub, we went to new bounds, we switched to new bounds. We never went back to original variable because it's simpler to work with u than that whole expression. Then we kind of used this little table to analyze what that one, oh, I already wrote it like that. Yeah, so we took that integral here, and then we did a little arcsine and analysis here. This probably may have been a little difficult part of this problem. But otherwise, both of these integrals are basic rules of integration, arcsine and u sub here, and power rule. Power rule is one of the basic rules for integration. And that is how you solve this definite integral. You can screenshot it if you want, but I will have the PDF down below as well.